Hi, I am Prof L and welcome to Chemistry Matters. And today we are going to further explore the mysteries, the many mysteries of carbohydrates. We talked last time, sort of in an introductory episode to carbohydrates, we talked about the use of Fischer projections, the fact that we could take a three-dimensional molecule and basically flatten it into two dimensions, okay? Now, when we've flattened a Fischer projection into two dimensions, we can't do anything with it. We can't turn it around or anything like that, okay? We can't certainly flip it from one side to the other because that's got certain implications in three dimensions that it doesn't have in two dimensions, okay? So just remember the Fischer projection is just basically making things easier for you, essentially. That's pretty much all that it is, okay? So we did finish off last time with a whole bunch of sugars, okay? A whole heap of sugars and Fischer projections of those sugars. And the most important thing in those Fischer projections, remember, they look something like this. We've got a CH2OH down the bottom. We have, in all of those cases, an aldehyde up the top, and this is the important OH here, okay? Depending on which side of the chain this OH is on, determines whether you are talking about a D sugar or an L sugar. That there would be a D sugar because it's on the right-hand side of the chain. If we had an OH there on your penultimate carbon, that would be an L sugar because it's on the left-hand side of the chain. Okay, so the bunch of sugars that we talked about were aldo or aldoses, okay? It sounds like you got a cold when you say that, aldoses. And aldoses have got aldehydes at the top of the chain. We can also have ketoses. Okay, we said that sugars, these sugar molecules could contain either aldehydes or ketones. And so a ketose will look something like this. So we will have a C double bond O there, and then we've got our usual 1, 2, 3, and we've got our CH2OH there. If we have our HO there, our OH there, and our OH there, then that makes a molecule that we would call D-fructose. And that, I'm sure, is, again, a sugar that you will have heard of. So fructose is an example of a ketose. And a ketose meaning that at the top of the chain, no, you don't have an aldehyde. You've got a ketone at the second carbon in the chain. Remember, you can't have an aldehyde, a ketone at the end carbon because that would then be an aldehyde, wouldn't it? Okay, so those are the differences between aldoses and ketoses. Okay, so this would be a 1, 2, 3, 4, 5, 6. This would be a ketohexose. Okay, and again, there's a whole bunch of ketohexoses as well, depending on the relative configurations at this carbon and this carbon and this carbon. Okay. Right, so here we go. Now, we have depicted our sugars, rightly or wrongly, as straight chain molecules. Okay? For example, we've got glucose here, so we've got a CH2OH, and we said, okay, so D-glucose, we've got OH there, we've got OH there, and OH there. So that is D-glucose. And you wouldn't be not mistaken, I guess, in thinking that the way that we've drawn that means that glucose exists as a 6-carbon chain. Okay, as a chain of carbon atoms. And you might think, yep, okay, that's reasonable. But, in fact, glucose is a cyclic molecule. Okay? It's not a straight chain at all. Well, about a little bit percent of it is a straight chain at any one time, but it is in fact primarily a cyclic molecule. And you're thinking, well, how does that work? How do we get a cyclic molecule out of that? Funny you ask. Funny you might ask that. Okay, so what we're going to take is this particular molecule here. Okay, so we're going to have a hydrogen there, and we are going to have an O and an H there. Okay, so what have we got? 1, 2, 3, 4, 5. So this molecule, 4-hydroxy, and this is an aldehyde, and so therefore it's a 1, 2, 3, 4, 5 carbon aldehyde, so pent-N-L. Okay, so why did we choose this particular molecule to look at? Well, it's got some of the features that all of those sugar molecules have got that we were just talking about. It's got an aldehyde at the end of the chain, obviously, because it can't be anywhere else. And it's also got an OH group elsewhere in the molecule, okay? At, dare I say it, the penultimate carbon in the molecule. This one here, that's your end carbon. This is your penultimate carbon. Now, what can happen here? Okay, well, the way that we've drawn it, not much, but let's redraw that, recognizing that we can get rotation around carbon-carbon single bonds quite happily, okay? So we're going like this, we're going to have the OH there, and that is our other carbon atom. So we've just redrawn the molecule now because we are going to put this oxygen of this OH group on carbon 4, 1, 2, 3, 4, we're going to put it close to this carbon here. Now, some of you may have learned in your organic chemistry courses thus far that if you've got a carbonyl carbon or a carbonyl group, we have got polarization in that group. So the oxygen is more electronegative than the carbon, so it's going to be pulling electrons towards itself, and that's going to make that carbon just a little bit positive, delta positive, a little bit positive. Now, what have we got here? We've got an oxygen atom of an OH group, and it's got 2 lone pairs on it. Now, those lone pairs are what we call nucleophiles. We will come across them in later videos, meanings of nucleophiles, etc. But in this case, it suffices us to know that if you've got a lone pair of electrons, okay, they are really going to like anything that has got a slightly positive charge. Remember, electrons are negatively charged. This guy is slightly positively charged, and so what can happen is that this pair of electrons can attack that carbon atom, and that can break the double bond to give you a single bond, and what you then end up with is something that looks like this. Okay, now how did we get that? Okay, so this oxygen here attacked this carbon to form a single bond, and this carbon-oxygen double bond then broke because the carbon atom would have more than 4 electrons if we didn't do that, and we pick up a hydrogen from probably this guy here, and that turns the doubly bonded oxygen into an OH. Okay, so we've now gone from a linear structure essentially, okay, or an acyclic structure to a cyclic structure, okay? This is what we call acyclic, meaning not cyclic, okay? And we have from this made now a cyclic structure. And really, really importantly, look at this particular carbon atom here, which is this particular carbon atom. It's the same carbon atom here, except what have we done to it now when we've made a ring out of it? look, we've got an OH attached, we've got an H attached, we've got an OR group attached, and we've got a carbon attached. We've got 4 different groups around that carbon. So this carbon is now chiral. We have created a stereocenter when we made the ring, okay? This carbon to start off with, okay, let's put the hydrogen in there as well, just so that, because remember that's an aldehyde. So this carbon here originally was achiral. Okay, it only had 3 groups around it because it had that double bond. But now we break that double bond, we bond in this oxygen, and now we've got a chiral carbon. We've made a stereocenter in making this cyclic molecule. Okay, so does this particular reaction happen? Yes, it does. Okay, this particular reaction occurs for 4-hydroxypentanal. Okay, you can do little studies and show that this is what happens. Okay, if it happens in 4-hydroxypentanal, then it's also going to happen in molecules that look very, very similar to 4-hydroxypentanal. In other words, your aldopentoses and your aldohexoses. Okay, you are going to get cyclic molecules formed from those, and those cyclic molecules are going to arise because of the attack of the OH on the penultimate carbon atom at the aldehyde carbon, like so, okay? And you end up with a cyclic species like this. Now, if we were going to name this particular functional group, what would we name it? We know that we started off with what we call, in this case, a difunctional molecule. It's got 2 different functional groups. It's got an aldehyde and it's got an alcohol. Okay? Now, the alcohol's gone, the aldehyde's gone. What do we call this? What is this? What type of functional group is this? Well, in this case, it is something called a hemiacetal. Okay, so, and you might want to call this indeed a cyclic hemiacetal. Hemi, what does hemi mean? Hemi is the same as semi. I don't know why they have 2 different names for that. Hemi meaning half of, so it means that you're halfway to an acetal. So we've got 2 new functional groups that we need to talk about in terms of sugar chemistry that are important. We have got C with an OH and an OR on the same carbon, or we've got a C with an OR and an OR on the same carbon. Okay, so this is called a hemiacetal, and this is called an acetal. Now you can see why we call this a hemiacetal and why we call this, well, you can't see why we call that an acetal, but you can certainly see why we call this a hemiacetal. It's halfway to an acetal. An acetal has got 2 R groups here, and R in this case are carbon-containing groups. So methyl, ethyl, butyl, whatever, okay? 2 of those OR groups on the same carbon give you an acetal. 1 of those OR groups and an OH group give you a hemiacetal. Okay, now those are incredibly important functional groups in all of sugar chemistry. Incredibly, incredibly important. So learn those particular structures because they will crop up time and time again. You'll be talking about things like reducing sugars, non-reducing sugars, and that all depends on whether you're talking about acetals, hemiacetals, etc., etc. Okay, so let's get back to sugars then. And so we've given you that example of 4-hydroxypentanal and showing how we can get that intramolecular reaction. Intra meaning within. So it's a reaction of a molecule with itself internally. That's cool. Okay, normally we think of reactions as being molecule A, molecule B, bang. Okay, this is molecule A that's essentially biting its tail. and forming a whole new molecule as a result of an internal reaction. Okay, so let's go back to good old glucose. And we learned that the structure of glucose looks something like this. So we've got the aldehyde here, we've got the CH2OH at the bottom, okay? And we've got the OHs and the H's all like this. The OH on the penultimate carbon is on the right-hand side, so that makes this D-glucose. Okay, so what can we do with this? Well, we can do exactly the same as we saw with the situation with 4-hydroxypentanal. We are going to take the OH group on the penultimate carbon, and we are going to have that attack this carbon atom here, the carbon atom of the aldehyde. And you might think, well, that looks miles away. How can it possibly do that? Everything looks to be in the way of that. It's not. Because let's redraw this. We're not going to necessarily draw the Fisher projection of this. Let's go and redraw it so that it looks a little bit more like real life. Okay? So this is carbon 1. That is your aldehyde carbon. Carbon 2, the OH points down. Okay? Carbon 3, the OH is on the other side and points up. Okay? Carbon 4, the OH points down. Carbon 5, we're going to have the OH pointing this way, and carbon 6, because it's D-glucose, we're going to have the CH2OH pointing up. Okay, don't worry too much about that last thing there. We will talk more about that later. Okay, so we've redrawn this to put this OH close to this carbon, and it works beautifully because you can see we've almost got a ring there. We can draw this molecule such that we've nearly got a ring. All that we need to do is to make a bond between that oxygen and that carbon. So the aldehyde carbon and this oxygen of this penultimate carbon atom here, okay? And when we do that, we do get a ring. And the ring is going to look something like this. Whoopsie, like so, and the CH2OH is going to be pointing up. We're going to have a down OH there, we're going to have an up OH there, we're going to have a down OH there. And now, this carbonyl, when this OH attacks, remember the carbonyl turns into an OH, okay? Now, what can happen is that that OH can be either pointing up, or indeed, it can be pointing down, okay? So we end up with an OH like that, OH, up, down, CH2OH, up, and we have got ourselves, again, what looks to be isomers, okay? So we'd have an H on that, we would have an H on that. Okay, because this is sugar chemistry, we give things a special name. So if you really want to be absolutely honest, these guys are diastereoisomers, okay? So they're not mirror images of each other, and so therefore they're related as diastereoisomers. But, as I say, because it's sugar chemistry, we give them a special name. We call these anomers, okay? And we call this carbon here the anomeric carbon, okay? If, and this one here as well, anomeric carbon. Right, so if you've got the OH on the same side as the CH2OH, then we call that a beta configuration. If you've got the OH on the opposite side from the CH2OH, we call that an alpha configuration. So there's yet more terminology for you. Sorry, but that's the way that they do it, okay? So we have made anomers, okay, which are, as I said, diastereoisomers. So this is what you would call the alpha anomer of glucose. This is the beta anomer of glucose, or to give it its full name, we would call this beta D glucose, and we would call this one alpha D glucose. Okay, the D referring to what side of the chain this OH is on, that's where we get the D from. We get the alpha and the beta from when we make the cyclic version, and the relative disposition of this OH versus this CH2OH. Are they on the same side of the ring, in which case you're talking beta? Are they on opposite sides of the ring, in which case you're talking alpha? Okay, I think, oh yes, one more thing. The D, if we've got a D glucose, then that means, or if any D sugar, that means that the CH2OH is pointing up. It's on the top side of the ring. An L sugar has the CH2OH pointing down. So just remembering this CH2OH is this CH2OH. That's where it comes from. Pointing up, we've got a D sugar. Pointing down, we've got an L sugar. Okay. I guess the other important thing to remember is that this oxygen here is this oxygen here. It's the oxygen from carbon 5. Okay, so the ring oxygen comes from this one here, the one that's either D or L. Okay. Right, that is an introduction to sugars. That's all that we're going to do, because by crikey, you think this is complicated. Wait until you start linking sugars together to get disaccharides and trisaccharides and polysaccharides and oh boy, yeah. Okay, so we will leave that for later on in your chemistry careers anyway, okay? So that's it for carbohydrates. Next video, we will be back with something completely different, I promise you, okay? So we will see you there. Take it easy.